review for chapters 3, 4, and 5. Well, they may not be exactly those chapters, but stoichiometry, solution stoichiometry, and thermochemistry for Dr. Segal's class. If you're not from Dr. Segal's class, you're still welcome to hang out and work on this with us. And I want this to be a student-centered session, which means I want, if there's any questions you have, please go ahead and tell me. I'm happy to go over any questions you may have. We're not going to have time to go through all of these tests, so we can jump around and focus on those things which you most specifically would like me to focus on. Furthermore, if you have any specific questions on a particular, or if you have any non-specific question on a particular topic, like, well, I'd really like you to go over X, Y, Z, you know, Hess's law or something like that, just let me know, and I'll jump to a question, or I'll come up with something that can go over that topic with you. Sounds good? All right, let's do this. So where would you like to begin? Net ionic equations. Okay, so that's going to be a solution stoichiometry type thing. We're going to go ahead and jump through here. And here's a couple of possible net ionic equations, or type questions. So the net ionic equation for the reaction between aqueous solutions of HF and KOH is what? So in a case like this, and I'm actually going to go ahead and Okay, so in a case like this, the first thing you'd want to do is you want to go ahead and write the reaction and predict the products. So in this case, reactants are going to be HF, which it says is aqueous. And I need to zoom in. Okay, HF, there we go. Aqueous plus KOH. And what does it become? Now here's the thing. It won't necessarily give you the products, but what you want to do is go ahead and identify what the charges of each of the reactants are. So for example, HF, what's the charge of hydrogen? +1. And what's the charge of fluorine? It is -1. If you look on the periodic table, you can tell from the periodic table, because fluorine is right next to that noble gas. It's going to gain 1 electron to be like neon, and therefore it'll become a -1 charge. So what about potassium? What is the charge of a potassium ion? +1. And don't overlook the polyatomics. OH is the polyatomic. So hydroxide, what's the charge of that? It is a -1. So there are certain polyatomic ions you should already have memorized. If you don't have them memorized, I would definitely strongly suggest that you do memorize them. And they would be, for example, NH4 plus, which is ammonium. They would be NO3, NO3 minus, nitrate, ClO3 minus, which is chlorate, C2H3O2 with a 1- charge, and that is acetate. And then, of course, OH minus, which is hydroxide, the one that we have down here. And then for our -2 ions, we have sulfate, SO4 2-. And you have carbonate, CO3 2-. And then we have our 1-3 ion that you should have memorized, which is phosphate. So why do I say you should memorize these 8 why not any of the others? Well, you definitely could memorize some of the others, and there are others that are important, but the vast majority of the time, you're given any sort of polyatomic ion in any of these questions, it's going to be one of these 8, or their derivatives. So when I said, what I mean by derivatives? Well, for example, the oxyanions like NO3, ClO3, if you take away one oxygen, it's still a polyatomic ion, still the same charge, but you take away one oxygen, like NO2 minus, the 8 is going to change to ite. So if you know nitrate, you know if it has one less oxygen, NO2, that means it's nitrite. And ClO2, likewise, chlorite. Or, for example, with SO4, sulfate, take one less oxygen, so SO3, that would be sulfite. So those would be like derivatives or derivative polyatomic ions. So you should know these 8 and also be able to recognize the derivatives, but I would say probably 95% plus of the time when you get a polyatomic ion on a test, it's going to be one of these ions or their derivatives. If we just look at this for a second, you can see that this is the case. ClO4, that's perchlorate, that's a derivative of chlorate. HF, you have hydroxide here. If I look up here, SO4, that's sulfate. Down here, NO3, that's nitrate. Nitrate again. You know, so you're seeing hydroxide, nitrate. So there's not a single polyatomic ion on this that isn't one of these 8 or their derivatives. Okay. So back to the problem. There's a +1 for hydrogen, -1 for fluorine, +1 for potassium, -1 for hydroxide. So this is a double replacement reaction. You recognize when you have like two ionics, or ionic-like types of things, this is going to be a double replacement. So the positive charges are going to switch places. So hydrogen from HF is going to go with what on the other side, for the other substance? OH, yep. So H is going to switch places with the potassium, with the K. They're not going to go together. You don't have like charges going together. Positive doesn't go with positive. They repel one another. But the H is going to go with the OH, and that's going to give you HOH, or H2O, water. So you have water on this side. That'll be one of your products. And then the other one will be what? KF. Now, KF, you're going to check and see if it's soluble. You might have a solubility chart. If a professor gives you, you might not. If your professor expects you to memorize some of the solubility rules, then you might just have to figure it out. I don't know if yours does or not. She wrote them down? Oh, okay, so you can just check and see if it's soluble. You'll find out that potassium is in fact always soluble. So the alkali metals, they're always soluble. And then water, of course, is a liquid, right? So that's the first step of writing the net ionic equation for this reaction. Now the second step is to break apart any aqueous strong electrolyte into its component ions. So that's provided, of course, it's balanced. In this case, it's already balanced. So first predict the products, number 1. Then balance the equation. And then split apart any aqueous strong electrolytes. So, number 1, predict products. Predict products to balance. And 3, split apart any aqueous strong electrolytes. Split. Now, what are the aqueous strong electrolytes? What sorts of things are aqueous strong electrolytes? There's only two things: soluble ionic compounds and strong acids. So this does require you to know what your strong acids are versus weak acids. So in this case, for example, when looking at HF and KOH, so HF, anything that has a hydrogen in front, that's an acid. So is HF a strong acid or a weak acid? Actually weak. There's only 7 strong acids, and you do need to have them memorized, unfortunately. So the 7 strong acids, I'll change my color real quick. 7 strong acids are HCl, HBr, HI, hydroiodic acid, HNO3, nitric acid, HClO3, HClO4, and H2SO4, the only diatomic, or not diatomic, but diprotic 2-hydrogen strong acid. Okay. All right. So those are your 7 strong acids. So you do have to know those. Anything that's not, only strong acids are strong electrolytes. Anything that's not a strong acid is not a strong electrolyte. It's going to be a weak electrolyte. So in this case, HF is a weak electrolyte. It's not one of the strong electrolytes. So therefore, it does not split up. It does not split up. What about KOH? Will that split? Is it ionic? Potassium's a metal, right? And OH is a nonmetal, right? Well, actually, those are the polyatomic ion. So metal, nonmetal? That's ionic. And is it soluble? Yes, it is. So it's ionic and soluble, and therefore it will split apart. All strong bases are going to be strong electrolytes as well. So, yep. No, you do split strong acids or bases. It's the weak ones you can't do. Now, for example, if you had something like aluminum hydroxide, if you looked at the solubility rules, you'd see that aluminum hydroxide does not actually split apart, but not because, and that's because it's not soluble. It's a solid. So you don't actually have to think about a special rule for bases, because the soluble-insoluble rule works sufficiently. Because all the bases that you're going to be exposed to, at least right now, later on that'll change, but the bases you're going to be exposed to right now are all ionic hydroxide compounds, basically, like some metal hydroxide. Okay, so what about water? Am I going to split that up? Water. Am I going to split water up? Remember, we only split up aqueous strong electrolytes, right? You're shaking your head. You're saying, no, that's right. And we're not going to split up water because it's not a strong electrolyte. It's not an aqueous strong electrolyte. So then what about KF? Is that going to be an aqueous strong electrolyte? Well, I split that up. Why do you say no? But is it an ionic compound? Is it an ionic compound? Yes. It's ionic compound, metal, nonmetal, right? Potassium. And is it soluble? Yes. Ionic compound, soluble, it's going to split apart. So The reason I distinguish between acids and ionic compounds is because, strictly speaking, acids are not ionic compounds. So you see the HCl, the HBr, the HF, those aren't ionic compounds because the nature of that bond is more covalent than it is ionic. But they do, the strong acids, it's so much like an ionic one that it actually does split apart in water. But ionic compounds are definitely a bit different. Okay, so we can now go ahead and split everything apart. So I split it up into its component ions. On this side, HF does not split up, so I will keep that together. And then I'm not going to bother writing the phases at the moment. KOH does split apart, so I'll put a K plus. OH minus doesn't, is the other part of that will split apart. And then I'll draw the arrow. Water stays together. And then potassium fluoride breaks apart, K plus, still a positive ion, and F minus. Okay. Now, if I was to add the appropriate phases here, let me go ahead and switch to this. Add the appropriate phases. This is going to be aqueous. This is aqueous. This is aqueous. Now, if you split something apart, if it came from aqueous, then it's aqueous. Now, the water is a liquid, so that doesn't split and doesn't change. K plus, KF was aqueous, so each of the ions is now actually aqueous. Aqueous means dissolved in water, and when they're dissolved in water, they split apart. Okay, so looking at this equation that I've written now, is there anything that's present on both sides of the equation in exactly the same way? The K plus. So the K plus, because it's present on both sides, I can actually cancel that out. I'm going to go ahead and cancel my K plus, and I'm left with HF plus OH minus is equal to water and F minus. That would be my net ionic equation. So in that case, I look down here, HF plus OH minus is equal to H2O and F minus. So the answer is B. Whoops. B, not C. Okay, there you go. Does that make sense? So that's how you break that down. Do you feel like you want to go over another example?
Well, I just have one question.
Sure, sure. Because it's a weak acid, and weak acids are not strong electrolytes. So when I was writing the steps for how to do these net ionic equations, so the first is predict the products. The second is balance the equation. Third is split aqueous strong electrolytes. And I guess I should add the fourth, which is cancel spectators. The spectator ions are anything that is present on both sides of the ionic equation, and it basically doesn't change. So cancel spectators. Now, if I left, here's a bonus question for you. If I left the K plus in there, what type of equation would that be called? Close. It'd be called the complete ionic equation. So there's the complete ion. There's the molecular equation. So this is your molecular equation. The HF plus the KOH goes to form H2O and KF. And then you have your complete ionic equation with the K plus. And then if you cancel out those K pluses, then you have the net ionic equation. And by the way, I have a bunch of cool practice problems on that you can totally check out. I also have answer keys, so I'm going to actually go ahead and type that in here. Let's do CCC, SE Science, or so you can check that out, or you can also go to You can also go to the Canvas page. It has all the same stuff. But basically, if I go down to under General Chemistry 1, Practice Problems, scroll down to aqueous reactions and solution stoichiometry, there's a section on meta-ionic equations that's pretty good, and precipitation reactions, meta-ionic equations. And the answer key is completely worked out. So you can see that, look at heaven. Oh, no, come on. No, not signing in. There. Ooh. Ooh. This is trash. Sorry. Anyway. Oh, there it is. So there's some practice problems. It has the magnesium chloride solutions mixed with sodium hydroxide. You write and balance the equations, and then break it up into complete ionic, and then cancel out the spectator ions. So there's complete answer keys for each one of these. And this is another one that I'll download. It just wants to be stupid. Anyway, and they're all worked out. So that's pretty cool. So going back to this, what's next? What would you like me to take a look at next for you?
Can you go over Hess's law of calorimetry?
Hess's law and calorimetry. Sure. I'll go ahead and jump to that. So, Chapter 5, Thermochemistry, Hess's law. Where's a good example of that? Okay, so there's a couple good examples. I'll go ahead and do problem number 15. It says, use the delta H values for equations 1 and 2 to determine the value of delta H for the equation 3. So when you're doing Hess's law, what you want to do is you want to look at the equation you're trying to solve for. In this case, use the highlighter. Yeah. In this case, that would be this equation right here. So this is the equation that I'm trying to find, okay? So what I like to do is I separate this by focusing on one substance at a time. So in the overall equation, I have N2 here, okay? There's N2, there's O2, and then there's NO2. So I'll first look at the N2 and say, which one of these equations, 1 or 2, which one of these equations has nitrogen in it, N2? The first one. And that's the only place you see the N2, right? So since that means all the N2 in the overall equation has to come from that first equation. Now in the first equation, is N2 a product or reactant?
It's a product.
Yeah, it's a product. So, but in the overall equation, what is it? Yeah, it's a reactant. So exactly. So if in this case, because it's on the wrong side, we have to flip the equation. So I'm going to go ahead and write that equation flipped, and that flipped equation is going to be N2 plus O2 goes to form 2NO. And if I flip the equation, what does that do to the delta H? It flips the sign, exactly. Because if you're going one way and it's releasing energy, if the reaction were to go the other way, it would be absorbing, right? That's going to flip the sign from negative to positive. So this is a positive 180 kilojoules now. Now, then I look at the next substance, oxygen. There's 2 oxygens, 2 O2s, okay, in the overall equation. Now, which of the above equations has oxygen, O2, in it? The first one, just the first one? No, also the second one, right? So both equations have O2. Since both equations have O2, I don't want to mess with that one. I'm going to skip that. I'm just going to go to the next one, okay? So just focus on those that appear only in one equation. That'll allow you to deal with this a little easier. So the last one is NO2. Which of the equations above has NO2 in it? Just the second one, right? And in the second equation, NO2 is a product, right? And in the overall equation, NO2 is a product. So then, all I have to do is write the equation exactly as it is. I don't need to change it because it's the same number. I need 2 NO2s in my product, and there's 2 NO2s in equation 2. So I have everything I need. I have exactly what I need here. I don't need to multiply it or flip it. So I have 2 NOs plus O2 goes to form 2 NO2. And the delta H, because I haven't had to change the equation, is just going to be the same as it was before, which is negative 112. Whoops. What?
Sorry, I got lost.
Okay. Which part did I lose you?
Yeah, when you're talking about the second one that you just underlined.
Okay. So in the case of the second one, so I skipped the oxygen because oxygen present in both equations, right?
Yes.
And so I go to NO2. NO2 is only in the second equation, correct?
Mm-hmm.
So how many NO2s are in the overall equation?
2.
And how many NO2s are in equation 2?
2.
2. So it's the same number, so I don't have to multiply anything. Now NO2 in the overall equation is a product or reactant? Product.
It's product.
Yep. And then in the equation 2, is it NO2 a product or reactant?
It's a product.
So in both cases, it's a product. So it's on the right side. It's on the correct side of the equation, and it has the correct number. So in this case, I don't have to modify equation 2. Equation 2 I can leave as it is.
Okay.
And then now that I have the equations appropriately modified or not modified, I check and see if adding the 2 equations together is going to give me the overall equation that I'm looking for. So in this case, if you notice the 2NO on the product side here and the 2NO on the reactant side here, if something is on both the product side and the reactant side, it cancels out. Okay?
Mm-hmm.
So then what am I left with? I'm left with N2. I have 2 oxO2 molecules, so I'll combine them, just say 2O2. And that's going to give me 2NO2. Now, is that the overall equation I'm looking for?
No.
Look at equation 3. That's what I'm looking for. Aren't they the same?
Yes.
Yeah, they're the same. So since the equation is, since they add together, they give this, when I add those 2 together, it gives me the overall equation I'm looking for. That means I can add the delta H's, and that will give me the delta H of the overall reaction. So delta H in this case, 180 minus 112, that's going to give you positive 68 kilojoules. Add 180 to negative 112, it gives me positive 68. So my answer in this case is going to be A.
So what is when we're solving for, I guess, the number 3, or if there's any other problem, let's say if it's like number 2 equation or whatever. So what exactly are we trying to do? Are we trying to match both of the reactions with
Well,
the one with the missing delta, or I guess I'm just kind of confused on how.
What you're trying to do is you're trying to figure out how to add these equations together to get them to give you the overall equation. Okay.
Okay.
What do you do to cause how can you change these individual equations with your known delta H's to give you the overall equation for the reaction? So like, for example, just as a quick example for number 14, and I won't take too much time with this, but in this case, I have 2E and O2 goes to form 2EO. That's a negative 3033 kilojoules, right?
Mm-hmm.
And then it has EO plus O2. It gives you EO3, and that's a delta H of negative 196. So what I do is I go ahead and I try to make these two equations so that they correspond and they'll add up to the overall equation. And the easiest way to do that is to match the amount in the overall equation to what is given in the equation here. See, I do it one substance at a time. And so in the case of problem 14, the first substance is E, liquid. So there's only one equation that has the E liquid in it, and that would be this equation here, right?
Mm-hmm.
And there's two E liquids in the overall equation, and there's two E liquids in the equation that I've circled. And they're both on the left side, they're both on the reactant side. So it's on the correct side, it's on the reactant side, and it has the right number. So I don't have to do anything to that equation. I can just leave it as it is and use the given delta H. Okay.
Okay, so let's say if it was on the product side, then you would have to flip the equation like you did on number 15.
Exactly. So if the E was on the product side, I'd have to flip the equation in order to make them match.
Okay.
And then the next part of this, I see oxygen is present in both of those reactions, so I'm not going to do anything with oxygen because that'll just get confusing. So then I go to the EO3. Well, the EO3 product here, this one right here, I see the only place you get EO3 is in this equation right here. And here it's on the product side, and on the overall equation it's on the product side. But notice that the numbers are different, right? The overall equation needs how many EO3s? 2. But in this equation here, how many EO3s are there? Yeah, there's only 1, right? So what do I have to do to this equation to make it match the overall equation? What do you think, Judy?
So I was writing down what you were saying. So I'm sorry, could you repeat the question?
So what would I have to do to this equation that I have the arrow pointing at in order to have it match the overall equation?
You would have to for the second one, right?
Yeah. I'm trying to match the EO3. There's 2 EO3 in my overall equation, and in this equation there's only 1. So what do I have to do to it?
Wouldn't you add the EO plus the O2?
No, I can't add anything. The only thing I can do is flip it or multiply it.
I don't know.
You have to multiply it by 2.
Okay.
Because, I mean, think about it. There's 2 EO3s in the overall equation, and therefore I need to get the second equation modified so that it gives me 2 EO3s. The only way to do that is to multiply it by 2. So then, if I wrote out those two equations, then I have 2E. This is equation 1. 2E plus O2 goes to form 2 EO3s, or 2 EOs rather. And then I have, if I multiply that second equation by 2, this becomes 2 EOs. plus O2. Hello. Doing Hess's law. All right, so 2 EOs plus O, and then this would also be 2 O2s because I will have to multiply everything by 2 in that second equation.
Mm-hmm.
And that's going to give you 2 EO3s. And so now you see, if I now add these two equations up, there's something that cancels out. What cancels out?
2EO.
Yeah, the 2EO, and then the product side here, reactant side here, it cancels out. And then if I add those two equations together, now it gives me 2E plus 3O2 goes to form 2EO3. And is that the overall equation I'm looking for?
Yes.
Mm-hmm. And because I multiplied that second equation by 2, I have to multiply the delta H by 2. And so the delta H then becomes the delta H of the first reaction, which was untouched, negative 333, plus 2 times the delta H of the second reaction, so 2 times negative 196. And then I add that together, and that's going to give me negative 725, if you do the math correctly. Ta-da! Does that make sense?
Yeah, it makes sense now. So you're saying that we can. So I guess for the second equation, we cannot. We can't. You said we can't add.
Yeah, we can't add anything to the second equation by itself. The only thing that we can do with a given equation is either flip it, products go on the reactant side, reactants go on the product side, or we can multiply it by a number. We can multiply it by 1/2, we can multiply it by 2, we can multiply it by 3 or 4. So we can multiply it, or we can flip it. But that's all that we can do. And then once we've multiplied it or flipped it, we can add them together to get the overall reaction. Because that's really what we're trying to do, because this is what Hess's law states. And you might get a concept question like this from your professor, so it's probably good to know this. But Hess's law basically states that if a chemical reaction can be carried out in multiple steps, then the overall delta H for that process is equal to the delta H for each step in that process. So in simpler terms, if I have 5 chemical reactions that add up to give me one overall reaction, if I know what the delta H is, the enthalpy for each of those 5 reactions, I can just add them up to get the delta H for the overall process, the overall reaction. Does that make sense? I'm not sure if I'm explaining it clearly.
Yeah, it makes sense after you showed it, because she was showing us this in class, but it made absolutely no sense. So now I understand it.
This is Hess's law is something that messes up a lot of people. No, there is a definitional thing that I would like to would like to take a moment to look at, and that's question number 16, the heat of formation. So what the heck is a heat of formation? Does anybody know offhand? Can they tell me? That's okay if you don't. It's a very specific definition. So I'm going to go ahead and write it down. But essentially, the heat of formation is the enthalpy required, and actually I'm not going to write it down because I can't write very well with this. No, enthalpy of formation is the enthalpy or the change in heat required to produce 1 mole of a product, exactly 1 mole of product from elements in their elemental state, in their standard state. So, in other words, what would be the standard state? And by standard state, I mean like normal pressure, normal air pressure, and about 25 degrees Celsius, so about room temperature. So what is the standard state of hydrogen? Would it be a solid, liquid, or gas at 25 degrees Celsius? H2, hydrogen. It would be a gas, right? And oxygen would be a gas. And nitrogen would be a gas. What about gold, the standard state of gold at 25 degrees Celsius? Solid. What about carbon, like coal or diamond? It's solid, right? So the standard state is it's the state that an element would have at 25 degrees Celsius under normal pressure. That's its standard state. So a heat of formation is the enthalpy accompanying the formation of 1 mole of a substance from elements in their elemental state. So which of these equations is a heat of formation? So one of these you could automatically rule out just by looking at the product. Which one is that? Which one of these is not an enthalpy of formation reaction? Well, it would be, it's A. Because that's 2 moles of product. It has to be 1 mole of product to be an enthalpy of formation. All the rest of them are 1 mole, but not that one. So we can cross out A. Now, at this point, we have to check the other one. They all have to be elements in their standard state, in their standard elemental state. So, N2 gas, is that standard elemental state? Yes. Oxygen, is that normally a gas? Yes, and it's O2. Okay. So it looks like B could be our answer. Let's take, looks like B could be our answer. Let's go ahead and take a look at some of the others. Carbon, is carbon normally a solid in its elemental state? Yep. What about, is hydrogen normally H? It's normally H2. Remember, there's those diatomic molecules, the Brinkelhoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, Brinkelhoff. So those 7 elements, Brinkelhoff, are diatomic when they're in their elemental state. So this is not standard state, and therefore that is not enthalpy of formation. What about phosphorus? Is phosphorus normally a gas? This would be harder to figure out because most of you haven't seen phosphorus, but you're right, it's not. Phosphorus, one example of phosphorus is red phosphorus, and that's like red stuff on the tips of matches. So that's a solid, right? So this should be a solid. This, of course, should be H2, right? So that should be Br2. So none of these are in their standard state. Here, carbon's a gas. Well, we know that's wrong, right? And then oxygen's an O instead of an O2. So the rest of these are all trash. The only one that's correct is B. That's what enthalpy of formation means.
Sorry, Mike, I'm a little confused on how you got B.
So, like I said, the 2 conditions for being an enthalpy of formation is enthalpy of formation is the heat accompanying the formation of 1 mole of a product from elements in their standard state, in the typical state or the normal state that they appear in, their stable state in nature. Okay? And so this requires you to know what the 7 diatomic molecules are, because H doesn't ever exist as, hydrogen doesn't ever exist as H, and Br doesn't ever exist as Br. It's always Br2 or H2. They're diatomic in their elemental state. So just looking at the diatomics, C, D, and E can be ruled out because you're not going to have H, you're going to have H2. You're not going to have Br, you're going to have Br2. You're not going to have O, you're going to have O2. So you can rule those out right away. A has 2 moles of product instead of 1, so that's not a valid heat of formation reaction. The only one of these that the heat of formation reaction is B, because it produces 1 mole of product, and oxygen, O2, it's in its elemental state. Nitrogen, N2, that's in its standard elemental state, in the gas state. And so that's how it works.
So, okay, so the product has to equal to 1 mole of the product, which is
Yes.
great.
It has to be 1 mole of product. Otherwise, A would be a heat of formation reaction if it was only forming 1 mole, because those are elements in their standard state. But the problem is it forms 2 moles, and therefore it's not a delta H formation reaction. All right, cool.
Okay, I got you. Thank you.
No problem. Next question. Any question? I'm taking all questions. It's open season. Throw anything at me. Okay. I thought somebody was going to ask me about the meaning of life. That's fine. So number 12 on the thermochemistry? Okay. So it said the specific heat, so this is the calorimetry, the specific heat capacity of lead is 0.13 joules per gram degree Celsius. How many joules of heat would be required to raise the temperature of 15 grams from 22 to 37 degrees? Okay, so this, whenever it talks about specific heat capacity, you're going to be using Q is equal to MC delta T. So this is actually an easy one if you remember this equation. Now in this case, we're asked for joules of heat, so we're actually asked for Q. So we don't even need to manipulate this. We can actually just plug in the numbers and solve. And so the mass is 15 grams. The specific heat, 0.13 joules per gram degree Celsius. And then we just multiply that times the change in temperature. Now, change in temperature is always final minus initial. Now, let me ask you a question. Can Q be negative? Yes, it definitely can. Q can be negative because Q represents what?
Heat.
It represents the energy change of a process, that your energy transfer of a particular process in terms of heat. So energy can be transferred by either heat or work. That comes back to that equation. The change in energy that occurs for a particular process is equal to Q, the energy change through heat, plus W, the energy change or energy transfer through work. So Q can be positive or negative, and if Q is negative, that means that you're losing heat energy. If Q is positive, that means that you're gaining heat energy. Or specifically, Q means that the system, if Q is positive, it means your system is absorbing energy. And if it's negative, it means it's releasing energy. So yes, Q is equal to MC delta T. So we have to check and see if it's positive or negative. It says you're going from 22 to 37. Here's your final temperature. Here's your initial temperature. Final temperature minus initial temperature. In this case, the final temperature is higher. So that means that the system is absorbing energy, and Q will be positive. And 37 minus 22 is 15. 15 times 0.13 times 15. That's going to give you some number that I don't know. 225 times 0.13. No, what? I don't know. 29. What'd you say? Oh, awesome. Yep, that's exactly right. Yes. So you'll sometimes see specific heat written as C. Sometimes you'll see it written as a little CS. And essentially, the C, the reason why it's called C is because it's specific heat capacity. It's the capacity or the ability of an object to hold heat. It can hold so much heat per degree Celsius change. So like this is why if you have a piece of aluminum foil in the oven at 400 degrees that you have a pizza on, right? You can actually grab that foil with your bare hands and pull it out of the oven at 400 degrees, and it's not going to burn you. But you get one drop of boiling water, which is at 212 degrees, on you, and it burns and it hurts. Why is that the case? Why is it that 212 degree drop will burn you, but a 400 degree aluminum foil won't? The water has a much higher specific, so for each degree temperature change, it holds much, much more heat, substantially more heat. And so what happens is when that water touches your hand, they both seek thermal equilibrium. So the heat from the water gets dumped into your hand, and the amount of heat causes your hand to get burned. The same thing happens with the aluminum foil, but because the aluminum foil, one, it's thin, but two, also, the aluminum foil is only able to hold like a little bit of heat for every degree Celsius. So, whereas basically that's why the amount of heat that it transfers is substantially less. That's just one example. So specific heat capacity, it's the capacity to hold heat. Whereas heat capacity refers to just the ability of an object to hold heat. Specific heat capacity refers to the ability of a substance to hold heat per gram instead of for the whole object. Okay. Any other questions? Yes. What's the what? Oh, yeah. So, I do have practice tests. I can go ahead and pull them for you. They're also available online. I'm going to be putting up the recording of this session and sending it out to y'all. So if you missed the early part of it, you can kind of catch up. Plus, by the way, I do have other session recordings you can feel free to check out as well, like for previous test reviews and things like that could be helpful. It's all up on our website. So what's next? What else can I help you with? Limiting reaction? Limiting reactants? Reagents? Okay. Limiting reagents. So let's go ahead and tap into that. We'll go ahead and skip over to practice test number 3. So there's a good limiting reagents problem, I think, in here somewhere. Here we go. So both of these, both 23 and 24 are good questions for this. 23 is actually more complicated. We can start with 24 if you want, and then come back to 23. So 24 basically states that it wants to know the number of grams of Al2O3 that could be produced from 2.5 grams of aluminum and 2.5 grams of oxygen. So I found the easiest way to deal with these limiting reagent type problems is to convert each reactant to the same product. Let me repeat that. We'll convert each reactant to the same product. So I'm going to go ahead and start with what my given is, and 2.5 grams of aluminum. So 2.5 grams, and I'm going to zoom this in just a little bit. Okay. 2.5 grams of aluminum. And what I want to convert to my product, grams of Al2O3. Now, what unit's going to come down? What unit's going to go on the bottom here? Grams of what? Aluminum. And what can I convert grams of aluminum to that will help me here? Moles of aluminum, exactly. Whenever I'm trying to change one substance to a different substance, I must use a mole-to-mole ratio. If I don't have moles, I have to convert to moles. So the grams of aluminum for moles of aluminum, now that I know I'm converting grams to moles, I can recognize that I'm going to need the molar mass of aluminum to convert grams to moles. If I look at my periodic table, it should be 26.98. That's the molar mass of aluminum. That's equal to 1 mole. Okay. One step done. Next, what's going to go on the bottom of my next conversion factor? Moles of aluminum. Note that I'm not putting any numbers. No numbers. Units first. Let the units guide your thinking, partially because if you don't know what units you're converting to and from, there's no way you can know what numbers to put. You don't even know what you're converting to. So in this case, I want to convert moles of aluminum to what? What'd you say? Oxygen? You could convert to oxygen, but if you were going to convert to oxygen, what would you convert to? Grams of oxygen, liters of oxygen, moles of oxygen? What would you convert to? Can't convert moles of aluminum to grams of oxygen directly. The only way to change the substance is what? To a mole to mole ratio. And so the only way to change the substance is a mole to mole ratio. That's the only way to change the substance. So I have to go moles of aluminum to moles of something else. Now, you could convert to oxygen, and that's another way to do these types of problems. But the way I recommend is convert to your product. Convert to the same product. And in this case, the product is aluminum oxide. So I'm going to go ahead and do that in this case. Now, how many moles of aluminum oxide are going to react with, or are going to be produced from how many moles of aluminum? What's the mole to mole ratio here? And where do I get it? What'd you say? 2 to 4. Yep. So 2 moles of aluminum oxide are produced from 4 moles of aluminum. Those are the coefficients of the balanced equation. They tell me what my mole ratio is. Okay, so now that I've got that, what's going to come down on the next conversion factor? What's going to be the unit that comes on the bottom here? Yep. There's that consistent pattern of conversion factors. Whatever was previously on the top is going to come down on the bottom. So if you keep that in mind, you already have half your next conversion factor every time you convert. All right, now what do I want to convert the moles of aluminum oxide to? Grams of aluminum oxide. I can only change the unit, moles to grams, if I have the substance being the same. Al2O3. All right. And then all I have to do is calculate, it's going to, a molar mass, grams to moles is always molar mass. It's going to be grams for 1 mole. And the molar mass is going to be 2 aluminums plus 3 oxygens. Basically, 48 plus 54. So that's going to be, 48 plus 54. Yeah, 102, roughly. Is that what you get? Do you get 102? Or 101.98? 101.78? 16 is fine for oxygen, but with aluminum being 26.98, it would be 101.96, according to my mental calculator. What did you say? 0.96? Okay. You might have just accidentally slipped the wrong number into the calculator. It's easy to make a mistake. And the calculator. Sounds good. All right, so now I can't do this in my head. Let's go ahead and multiply 2.5 times 2 times 101.96 divided by 26.98 divided by 4. So basically multiply everything on top, divide by everything on bottom. What do we get for our answer? I'm sorry? 4.7. So in this case, we get 4.7 grams of product. And that's aluminum oxide. Let me go ahead and drag this over a little bit. Oh, no, I ran out of room.
Hey, Mark, I had a question. So are we?
Nope.
We're not solving for oxygen.
No, you're not solving for oxygen. What we want to do, we're trying to calculate the number of grams of aluminum oxide that could be produced. So what we do is we take each reactant, convert to the same product. Whichever one gives me less product, that lesser amount of product is the amount that's going to be produced.
Okay.
So we're basically going to do the same thing. I'm actually going to run through this.
Ouch.
You okay there? Okay. Right, there we go. And so I'm just going to go ahead and I'm going to do the same thing with grams of oxygen. Now this is going to be a very similar process for convert grams of oxygen to moles of oxygen. Then I'm going to convert moles of oxygen to moles of aluminum oxide. And then I'm going to convert moles of aluminum oxide, back to grams, moles of aluminum oxide back to grams. So moles of Al2O3. Talking too fast. Moles of Al2O3. And so 1 mole is equal to 32.00 grams of oxygen, because oxygen is 16. And then the ratio is 3 oxygen molecules for every 2 moles of product. And then 1 mole of O2, I already know that molar mass, it's 101.96. And then I just go ahead and multiply everything on top and divide by the bottom. And what does that give me? $10.60. Yes. Yes. I just know. No, I don't know. It might not be wrong. Let's see. It feels like it should be wrong, though. Yeah, it's wrong. Yep. So, what'd you say? 5.30. Give me that calculator. I don't trust you guys anymore. You failed me. Divided by 32 times 2 divided by 3
Wait, 32. Why 32?
times 101.96. Oh, it is 5.31. Okay. I forgive you. You're forgiven. All right, so 5.31 you said? Or 5.3? Okay. So notice both 5.3 and 4.7 are up here. So which one of these answers is correct? The smaller one, that's right, because what happens after 4.7 grams of oxygen is produced, 4.7 grams of aluminum oxide is produced, what happens? You run out of?
You run out of aluminum.
You run out of aluminum. So the reactant that produces the lesser amount of product is your limiting reagent. So this bad boy right here, this is your limiting reagent. This is your LR. All other reagents are your excess reagents, in this case oxygen. So the limiting reagent always tells you what your, wait for it, theoretical yield is. Theoretical yield. Because these calculations, real world isn't quite as neat and nice. Sometimes things don't react completely. But this calculation indicates is that if I had 2.5 grams of aluminum and 2.5 grams of oxygen, and they reacted to the greatest extent they possibly could, they react completely, it would produce 4.7 grams of aluminum oxide. So if under perfect conditions they reacted totally and you were able to collect all of it, you would get 4.7 grams of aluminum oxide. So that's why they call it your theoretical yield. In this case, they just say that could be produced. So that means it's implying theoretical yield. Now, like in the previous problem, however, it says a reaction of 3.82 grams of magnesium nitride with 7.72 grams of water. And it said it produced this. Well, this 3.60 grams of aluminum oxide here, this is what was actually produced. This is your actual yield. Actual yield must always be given, whereas theoretical yield must be calculated. So in this problem, we just solved for the theoretical yield, and that's our answer, 4.7. In problem number 23, you would do the same thing, except there would be an added part to it. You'd have to take your answer and solve for the percent yield, which is, anybody remember the equation offhand? You got it. Actual over theoretical times 100%. There you go. Now the actual, of course, is going to be 360. Your theoretical is going to be whatever you calculated from your limiting reagent calculation. Convert each reactant to the same product, and then whichever one is the lesser one, that's your theoretical yield.
So we would convert magnesium nitride and water to the
Yeah, so
magnesium oxide?
exactly. So convert grams of magnesium nitride to grams of magnesium oxide, and then convert grams of water to grams of magnesium oxide. Whichever one produced less magnesium oxide, that's your limiting reagent. Or that's your theoretical yield, yeah. So that's how it works. And by the way, I have all of these tests completely worked out with all of the work shown up on our website. So I'll make sure to go over to how to find that in a little bit. But with the time that we have left, I'd like to try and see if I can answer a couple more questions for y'all. What other questions can I answer for you? And of course, it doesn't have to be from one of these tests. It can also be from your book, or it can be from.
Hey, Michael, quick question. For number 23, did you have to find the limited reagent first?
Well, you have to find the theoretical yield.
Okay.
So, for example, basically, I would take my 3.
So it doesn't matter which gram we would use, either the 3.82 or the 7.73?
No, you have to use both.
Oh, you have to use both?
Just to show you real quickly, because I actually have this practice test up on our website. I'll show you quickly so that I don't waste too much time, or I don't, not waste, but I don't want to spend too much time drawing it out manually, like when I can just go ahead and do this. All right, come on, do it. Do it. There we go. Here we go. Yeah. So here's 23. So yeah, I would take 3.82 grams of magnesium nitride, and then I would go ahead and convert it to grams of magnesium oxide like this. Grams to moles, moles to moles, moles back to grams. And if I convert each of those to product, I see that the water would give me 17.3 grams of MgO, whereas the magnesium nitride would only give me 4.58 grams of MgO. So the lesser amount, that's my theoretical yield. And the amount that produced it, this is my limiting reagent. You're welcome. Okay. Okay. And this would be my limiting reagent, the Mg3N2. And so then I just take my experimental or actual amount divided by theoretical or calculated amount. And that's going to be the 3.60 that's given in the problem. Your actual yield must always be given. And I'm going to divide that by my calculated one, 4.58 times 100%, gives me 78.6%. Titrations? Yes. Okay, so there's two ways to do titration problems. There's what I like to call the easy way, and there's also the hard way. So, which way would you like to learn? Good choice. All right, so let's say, for example, here actually, I'll pull an example from here. That'll probably be the fastest thing I can do. Practice problems, and there's aqueous titration problems. Here we go. Wait, what? Pay no attention to the man behind the curtain. Hold on. I am the great and powerful Wizard of Oz. Oh, wait, let's see. Oh, there we go. Titration problems. Here we go. So, titration problems work kind of like this. Basically, if you're given a certain amount of acid, and you have to calculate a certain amount of base that reacts with it, you can do so by using what's known as the titration equation. So that's this thing up here. The molarity of the base times the volume of the base is equal to the molarity of the acid times the volume of the acid. So let me download this real quick. Open file. All right. Zoom in. So in this case, so I'll work an example for you real quick. In this case, it said this many this molarity, 0.53 molarity of hydrochloric acid required 76.02 milliliters of 3.1 molar aluminum hydroxide. So you're trying to figure, in this case, now the question you would get would be like, how many milliliters? It wouldn't be worded so vaguely as this one is, but say, how many milliliters? Many milliliters. So how many milliliters of hydrochloric acid is required to react with 76.02 milliliters of 3.1 molar aluminum hydroxide? So I'm looking for the volume of the acid, right? And, well, that's not the volume of the acid, sorry. I'm looking for the volume of the acid. Now, what is NH plus? That's the number of acidic hydrogens. What is NOH? That's the number of OH minuses that are present. So in this case, MH plus is the molarity of the acid. In this case, the acid is hydrochloric acid, which is HCl. Okay, so you should all be familiar on how to name acids and write the formulas, right? Okay, so HCl, the concentration is 0.53. How many acidic hydrogens are present in HCl? 1, exactly. So the volume of the acid times 1 acidic hydrogen. Now, if I look at aluminum hydroxide, the formula for aluminum hydroxide, aluminum's a +3, hydroxide's a -1, so this is ALOH3, right? So the molarity of the hydroxide is 3.1, right? Molarity of aluminum hydroxide. The volume is the 76.02 milliliters. And the number of hydroxides in aluminum hydroxide is how many? 3. So then all you have to do is solve for the volume of the acid by dividing both sides by 0.53 and 1. And that will give you your volume of the acid. Now you could also be asked for the molarity, or you could also be asked for, yeah, I mean, so that's typically what you're going to be asked for, either molarity or volume.
So that's a little bit confusing because how do you know which side to put the volume on?
Well, so the volume of the, so it doesn't matter if you put the acid on the left and the base on the right, or the base on the left and the acid on the right, so long as you keep the acid and base, all the acid stuff on one side and all of the base stuff on the other side.
But that's what I'm saying, like, how do I know that the
There's 76,
76.02 goes on the...
because it says 76.02 milliliters of 3.1 molar aluminum hydroxide. So that means that that is of the base. Does that help? Yeah. So look for those context clues, and so yeah. And actually, sorry, this should just be 1, not VH. So bye bye, and then bye bye, and then it's gone, and then you get your answer, the volume, which is going to be like obscene in this case. But yeah, that's how you solve for a titration problem like that. Otherwise, what you can do is you can write and balance the equation, and then do solution stoichiometry, which is basically, in this case, I mean, I can kind of show you what that would look like. For the problem that I just did above, I would basically do aluminum hydroxide plus HCl, and then I'd have to predict the products, which would be aluminum chloride and water. And then I'd have to balance the equation. So it'd be 3 waters and 3 HCl's. And after I wrote and balanced the equation, which would take you guys longer than it takes me because like I can whip through this pretty fast just because I have so much experience with it. Then I would take, so I'm doing the same problem we did. I'm doing problem 1, not number 2. But then what I would do at this point is I'd take the volume and the molarity that I'm given and use that. So I would take 76.02 milliliters. Then I'd convert milliliters to liters because molarity is moles per liter. And so that'd be 1,000 to 1 liter. Then I'd convert liters to moles using the molarity. So that'd be 3.1 moles of aluminum hydroxide. I'm getting the feeling you're probably already recognizing that this is not probably the way you want to do it. And then once you have moles of aluminum hydroxide, you can convert moles of that to moles of HCl, because I'm trying to get the volume of HCl. Moles of aluminum hydroxide, AlOH3. But it is valuable to know this because you will occasionally run into situations where you do have to kind of use this method if it's like not a titration. So moles of AlOH3 to moles of HCl, according to the balanced equation, it's a 3-to-1 ratio, so 3 moles of HCl to 1 mole of this. And then I can use my molarity of HCl to convert moles back to liters. So moles of HCl per liter. So 1 liter is equal to 0.53 moles, because molarity means moles per liter or moles per 1 liter. I just use that molarity up here. And then I can convert liters back to milliliters to get my final answer. And there you go. And sometimes So, I mean, this will give you the same exact answer as the above way will. And sometimes I like to write the titration equation more like this. I just say molarity of the acid times the molarity of, times the volume of the acid times the number of H pluses in the acid formula. And that's equal to the molarity of the base, MB, times the volume of the base, BB, times the number of OH minuses in the base. Now, notice also that this equation is very similar to the dilution equation. M1V1 is equal to M2V2. So you'll use, if you're diluting something, you can just use M1V1 is equal to M2V2. This is just a slight expansion of that because it takes into account the number of H pluses and OH minuses in the equation. But usually, even with the titrations, they'll be monoprotic. I mean, in other words, NH plus will be 1 and OH minus will be 1. And so you could literally just use M1V1 is equal to M2V2 if you wanted. But you can't always use that. Sometimes professors likes to throw the 2 H pluses at you or H3PO4, in which case you have to kind of like, well, I guess I'm going to have to use the other. All right, cool. Any last quick questions? Oh, the titration? Sure, like you want to do maybe the acetic acid versus strontium hydroxide one, number 5. Okay. Well, first acetic acid is HC2H3O2. And strontium hydroxide is SrOH2, because strontium is a +2 charge. And that is a strong base. Okay. So using the titration equation here, I want to know, in this case, it's giving me the volume of the acid. I need to solve for the molarity. And in your case, your professor would explicitly ask you, please solve for the molarity, or what is the molarity of this equation? So I'm looking for the molarity of acetic acid. So the MA is what I'm looking for. The volume is 49.8. Nope. And that's the nice thing about the titration equation. As long as the volumes are the same unit, you don't need to put it in any specific unit. If they're both gallons, that's fine. If they're both quarts, that's fine. If they're both milliliters, that's fine. Whatever, as long as the unit is the same, then you're okay. If the units are different, then you have to convert one of them into the other and make them the same. So 49.8 milliliters. And how many acidic hydrogens are in HC2H3O2? Acidic hydrogens are always listed at the front. It's 1. Not all the hydrogens in acetic acid are actually acidic. They don't always give up their H plus. The H3, only one of, and acidic hydrogens, and when you write out your acid formulas, they're always put in the front, so it's easy to identify it.
So if it's not in the front, it's not
It's probably not, it's probably not acidic hydrogen. And then, so on the other side, then the molarity of the strontium hydroxide is 1.45. And then the volume of the strontium hydroxide is 27.1 milliliters. And then the number of hydroxides in strontium hydroxide is what? 2. And so then, to solve for molarity, just divide both sides by 49.8 and you're good. All right, cool. Well, before I let you go, I just want to show you one more thing real quick.
Michael, sorry to cut you off. For those titration calculations, how do you know what you're needing to solve from the formula?
It would tell you. It would tell you. I mean, you could just plug in what you have and then see what you're missing and then solve for that. But these questions are rather ill-defined. This is from a worksheet that I was given, and I went ahead and I put it up there because I didn't have anything else specifically targeting titrations. But usually you'd be given it, or you'd be told, it's like, what is the molarity or what is the volume of? Okay,
Okay, thank you.
no problem. Okay, so one more thing before I let you go. I want to show you something cool. Okay, so either on, so if I go to www.tcc.d.edu, edu. So you can either access this just by Googling TCC SE Science and it'll come to our little website here. It's also up on the Canvas Learning Commons. So if you go to Academics under tccd.edu, scroll down to Academic Help, click on the Labs and Tutoring button, and then click on Virtual Learning Commons in Canvas. That will pull you to Learning Commons. Then you can click on Science Support, and then when you go down here, then you can click on Chemistry. Now, admittedly, that's a lot of clicks. So if you want to just Google TCC SE Science, that might just be a little bit easier, I don't know. But one of the things I want to show you that we have here is for the practice test that we use practice test for Chemistry 1411. We used Dr. Segal's 3, 4, and 5. And I already showed you what those complete answer keys look like. Shows all the work and everything. So definitely check that out. Like I said, complete practice test, complete answer keys. In addition, in our workshops and events tab, if you go to archived workshops, because this site is now unfortunately dead, and they keep on like delaying switching it over to the new version. But anyway, you can still look at the archived archived workshops. And so for archived workshops, there are actually a bunch of test reviews in here. So if you wanted to, and there's also what are learning workshop videos. So if you wanted to just have a session on stoichiometry and solutions, or if you wanted to go over thermochemistry, there's thermochemistry 1 and 2. And it goes into them a little bit more detail than we were able to in this review session. The most recent collection is down here, spring 2021. This is the most recent collection of learning workshop videos. So it has one over stoichiometry, net ionic equations and solution stoichiometry, thermochemistry 1, thermochemistry 2, and here's a test review, thermochemistry and the gas laws. But yeah, so if any of those can be helpful, that's cool. Please feel free to check those out. There's also individual tutoring videos as well, a video tutorial library for Chemistry 1411. Click on video tutorials, and it has like solution stoichiometry, aqueous solutions. It has specific, relatively short videos on how to do each type of these problems, how to predict products, how to do oxidation numbers, how to do molarity problems, how to do dilutions and solution stoichiometry. The thermochemistry, you have some relatively short videos here going into detail on all these different things like what is thermochemistry, what are the basic definitions, what's first law, what are state functions versus path functions, what's enthalpy, endothermic versus exothermic, different calorimetry, all that kind of stuff. So Hess's law, all that kind of good stuff. So just tons and tons of resources up here. And as always, you can feel free to go ahead and email me at any point, and I'm happy to help you with that as well. No problem. When's your test? Tuesday? Okay, I'm glad it's not tomorrow because I don't think I'm going to be able to get this uploaded and sent out to you by the time I leave at 10 minutes. All right, well, thank you so much, and you guys have a great day. Thank you for coming. You're welcome.